Hi everyone, my name is Ingao. My presentation is about broken spike detection using ultrasonic testing. Before my presentation, I would like to acknowledge my colleague Dr. Anish Poudel and Cameron Stuart from the Federal Railroad Administration for the support in this study. In the presentation, I will first provide a quick overview of the broken spike issue, why we need NDE methods to address this problem, and what we want to achieve from this study. After that, I will present the research findings through ultrasonic testing simulations, laboratory testing, and in-track testing. Findings and potential future work will be presented at the end. Broken spikes have been observed in elastic fastening systems in both revenue service and FAST. An elastic fastening system provides a clamping force between rails and the tie plates using elastic fasteners. It has higher railroad resistance and higher gauge strength than the arima plate cut spike system. Therefore, elastic fastening systems are often used on high degree curves. Some typical elastic fastening systems are shown in the left bottom of this slide. Mechanically, these systems behave differently than cut spike only systems. Broken spike issue is found on these types of fastening systems on the high rail of high degree curves for both cut spikes and screw or drive spikes. This slide presents the findings from a field survey conducted by a Class 1 railroad. This survey was conducted on 70 different curves. All spike positions on the high rail side were inspected. Broken spikes were found on field and gauge sides and anchor and rail spike positions. The survey also collected data from automated inspections by track geometry cars. As shown on the right, the track geometry data indicated a gauge widening from 0.7 inch to 1.2 inch at one curve over a 1-year period in this area where broken spikes were found. Also, fretting and wear were found where the spike shaft contacts the spike hole on a tie plate. The metallurgical analysis indicated that the material fatigue is the failure mechanism. The failure plane is consistently about 1 to 1.5 inches below the top surface of the tie for cut spikes. Screw or drive spikes typically break at where the thread starts. The loading applied to spikes come from dynamic train forces and static forces such as thermal-induced forces in rails. According to the previous modeling work and field observations, broken cut spikes are caused by a combination of effects of the lateral and longitudinal forces that are transferred into the fastening system. The combined forces generated stress concentrations on the spike edges where fatigue cracks have been shown to initiate. The location of the height stress aligns with where the actual failure occurs. The current practice to find broken spikes in track is to knock or kick the spike to see if it is loose or makes an unusual sound. This is very time-consuming. Also, this method cannot be automated while railroad industry seeks an automated inspection eventually. This is the motivation of this study to investigate an ultrasonic NDE approach for broken spike detection. This research study has two main objectives. First, to perform the optimization of the ultrasonic parameters using a modeling approach to detect broken spikes. Second, is to conduct proof of concept experimentation and validation in a controlled environment to test the effectiveness of the detection. The first step in this study was to use an UT simulation approach to optimize the ultrasonic parameters for efficient and effective flaw detection in spikes. Appropriate transducers were selected for laboratory and in-track testing based on the simulation results. SIVA software was used to perform this simulation. The software can simulate an ultrasonic beam field in an object with any geometry. As shown on the right, the source of the ultrasonic beam was located on top of a spike to simulate how an actual transducer is placed. By obtaining the signal amplitude at the depth of interest, we can find what ultrasonic parameter will be most suitable for the spike breakage detection. This slide shows the test parameters used for this UT modeling. Both cut spikes and screw spikes were included in the simulation. We explored several UT parameters. We had two transducer types, single element and dual element transducers. And we had two different transducer diameters, a 1/4 inch and a 1/2 inch. Also, we have four different transducer frequencies included in this model. And for dual element type transducers, roof angle is a key parameter, and we had 6 different roof angles in this modeling. For the single element simulations, 4 transducer frequencies and 2 diameters were simulated. This gave us a total of 8 simulation cases. The signal amplitude at 4 inches from the spike head was evaluated. Signals less than -10 dB attenuation at that depth were considered as acceptable. From the results, 5 MHz half-inch transducer and a 10 MHz half-inch transducer generated acceptable signal amplitude at the desired depth. Both cut spikes and screw spikes had the same results. For the dual element transducers, the roof angle is a key parameter. The roof angles varied from 0 to 5 degrees in the simulation. The plot in this slide shows the simulation results from a 10 MHz half-inch dual element transducer. As we can see, the smaller the roof angle is, the higher the signal amplitude is. The transducer with 0 roof angle generated the best signal of all 6 cases. 1 degree roof angle was acceptable as well. However, when we reduced the transducer frequency to 5 MHz, only the transducer with 0 degree roof angle had acceptable results. Transducers with other frequencies and diameters did not have acceptable signal amplitude. Two key findings are summarized in this slide based on the simulation results. The first is transducers with half-inch diameter, half MHz to 10 MHz can generate acceptable ultrasonic beam responses at the desired depth. Secondly, for the dual element transducers, 0 degree roof angle is recommended. The transducers recommended by the simulation effort were further tested in a laboratory condition. Transducers 1 and 2 were the ones suggested by the simulation results. We also selected 3 other transducers. Even though they did not have acceptable signal responses in the model, we still tested them to compare the results and validate the findings from the modeling. For the testing, we connected the transducers to a flaw detector. The spikes were fitted into a tube to hold it in place while being tested. The transducer was placed on the spike head directly over the spike, as shown in the left photo. A conventional handheld contact UT method was used for the testing. Spikes that failed in service and spikes with electrical discharge machining notches, we call it the EDM notches, were used in the laboratory testing. EDM notches were used to see if the UT approach can detect a halfway crack, and also were used to understand the effect of the angle of failure planes. 3 cut spikes and 3 drive spikes were cut with EDM notches with different orientations. The notches have a thickness of 5 mils halfway through the cross section. The orientations of the cutting planes are 0, 10, and 20 degrees with respect to the horizontal plane. The EDM notches spikes were mainly for demonstration and calibration purpose. The right picture shows an example of the flaw detector results, called A-scan results. It was generated by a half-inch 5 MHz dual-element transducer on a cut spike with 0 EDM notch. The x-axis is the distance on the spike shaft from the spike head. Y-axis is the signal amplitude, ranging from 0 to 100% of the full screen height. We can clearly see a signal spike at 3 inches from the spike head with an amplitude of 62% of the full screen height. This indicates that the spike cracked at 3 inches from the spike head. This is how we identify a broken spike and the location of the failure using this UT method. The spikes were tested using the test procedure described earlier. This slide shows the findings from the laboratory test. 3 transducers generated acceptable indication were chosen for the further in-track testing. The lab test also showed that the signal amplitude decreases as the orientation angle of notches increased. As listed here, 3 transducers that showed acceptable results in the laboratory test were included in the in-track testing. A blind test was conducted on 3 types of spikes. 10 of each type were selected and marked for the in-track testing. For each type of spikes, there were 2 broken spikes, 2 spikes with a notch cut, and 6 good spikes. The same test procedure for the lab test was followed for this in-track test. This table in this slide shows the detection results. The half-inch 5 MHz dual-element transducer reported all the cut spike conditions correctly, while all the other test cases had error indications. The half-inch 5 MHz single-element transducer did not show indication for the 2 notched spikes, but reported broken and good spikes correctly. This might be acceptable since the transducer was able to identify broken spikes without errors. This finding also verified the simulation results since these 2 transducers were recommended by the modeling work. None of the transducers reported drive or screw spike conditions correctly. To summarize this presentation, according to the lab and in-track testing, 5 MHz and a half-inch dual-element transducer showed its effectiveness of detecting broken cut spikes in the laboratory and field conditions. None of the tested transducers could report the drive or screw spike conditions without errors. And potential future work based on the current study could be testing a 10 MHz half-inch transducer. Recall the findings in the UT modeling. A 10 MHz half-inch transducer was the one with the best signal indication. However, due to the transducer availability, we could not get the optimal transducer for the testing. Therefore, a 10 MHz half-inch transducer is worth being tested in the future study to see if it can improve the spike detection. Lastly, I would like to mention some testing related to the spike breakage study. We developed instrumented spikes to characterize the spike loading environment under train passage to further understand the failure mechanism. Also, we are evaluating several remediation methods at TTCI, such as using rail anchors using curved block plates. Thank you very much for watching this presentation, and I would like to take any questions if there's any. Thank you.